Okay, so a lot of days what I would do is when you come in the door, I'd have a problem or a handful of problems up here for you to work on to review what we did yesterday. Since yesterday was our first day, we really don't have anything to review. So we'll start in with new material here. So we talked yesterday about that idea of a count and a name, and then we talked about place value and how place value holds everything together. And we looked at having expanded forms or the full form of numbers, like 274 is really just an abbreviation for 200s, 7 tens, and 4 ones. And when we have them written out that way, the reason we do our operations the way we do makes a lot more sense. We talked yesterday about addition and subtraction, where we have to have the same name. We can only combine things with the same name when we add and subtract, and then we keep the same name. However, when we multiply or divide, we also combine the names, which implies we don't have to start with the same name. So if I'm going to do an addition problem, like 274 plus 314, I'm going to write that one out in long form as well. It says 300s, 110, and 4 ones. When we add numbers, it's always been drilled into us that we have to line up our columns so that we can add straight down our columns. Why is that? Well, when we add numbers, we can only combine things that have the same name, and that goes down to each digit. We said that each digit here has a count in the name. This isn't just a 7, it's 7 tens. Well, when we add or subtract, we can only combine tens with other tens, ones with other ones, hundreds with other hundreds. That's why we have to line up our columns. Once our columns are lined up, we just have to add or subtract straight down those columns. So 2 and 3 makes 500, 7 and 1 makes 8 tens, 4 and 4 makes 8 ones, 588. Now you might be looking at that thinking something looked a little strange about how I did that. Anybody pick up what it was? I started on the left and I went to the right, didn't I? I went this way as I added. How would we normally do it? We start at the end. We start at the right side and work our way back to the left. Why do we usually do it that way? In case we have to roll over or carry numbers. Exactly. We run into things like this. 578 plus 259. And I'm not going to write them out in the long form, full form this time. I'm just going to go ahead and add them. We usually start on the right and work our way back to the left because 8 plus 9 is 17. We can't have 2 digits there, so what do? We carry the 1 and we keep the 7. So now 1 and 7 is 8, plus 5 is 13. Keep the 3 and we carry the 1. 1 and 5 is 6, plus 2 is 8. So 837. Now, believe it or not, carrying is a relatively new process. Now, by relatively new, I mean a couple hundred years old. Before that, and I'm not expecting anybody to change how they add numbers, and I'm just showing you this to make a point. Before that process of carrying was developed, one possible way of adding these would look like this. 5 plus 2 is 7. 7 plus 5 is 12, so 2 drop the 1. 8 and 9 is 17, so 7 drop the 1. 837. I'm not showing you that to change how you add numbers. I'm showing you that to make a point. We've always been taught that there's only one right way to do things in math. That's not true. There's several ways. I could actually show you 3 or 4 other ways to add numbers that'll work every time. I'm not going to do that because I don't want to confuse you, but there are several ways of doing it. Now, on the realistic side of it, there is a quiz you guys will take probably next Tuesday where the first 6 questions of the quiz, I don't let you use a calculator. I want you to do them by hand. And what I'll do is I let you check them with a calculator, but you have to show the step-by-step work to add them, subtract them by hand. After that, we're going to let you use the calculator for everything in here. But if you're doing this on the calculator, I would hope that you would do, okay, that's about 600. That's about 300. 6 and 3 makes 9. I'm expecting an answer around 900. Because if you're like me, I've got these fat sausage-like fingers. I'm punching keys on the calculator. It is not uncommon for me to do something like this. $6,037. What did I do wrong there? Hit the 7 twice, or when I went to hit the 8, I hit the 7 again, or whatever. I hit more than one key at a time. An unintended key got hidden there. If I'm not paying attention, I'm just punching numbers in the calculator. It spits out 6,037. I might write that down and just go on with life. So before I punch those numbers in, it's best to think about it. Okay, 6 and 3 makes 900. Something actually a little less than 900 works for me. If I'm rounding both of those up, I know that's going to be a high estimate, right? Or the other thing that happens a lot is this. Calculator buttons get tight or whatever. I used to work on a lot of construction sites doing structural engineering. I'd get sand in the keys all the time and they wouldn't work. They get sticky, yep, so you go do something like this. Well, you can see there the 7 didn't register when I hit it. Press the key, it just didn't register. And if I'm in a hurry, I'm not looking up there to see whether the 7 comes up on the screen or not. 317 gets written down, that's obviously not the right answer. So I mean, this estimate isn't going to catch every mistake, but it'll catch a lot of the really bad ones. It still doesn't catch if I accidentally go to hit a 6 instead of a 5 or whatever when I'm punching it in. It's probably not going to catch that. Subtraction. I'm not going to write this out in full form because I think you guys get the point by now that adding or subtracting, you have to line up those columns because you can only combine things that have the same name. And that goes down to the place value. So we're going to subtract. 5 minus 2 is 3. 8 minus 6 is 2. 4 minus 1 is 3. Well, what did I do there again? I went left to right. Normally we go the other way in case we have to. Well, similar to carryover, what we subtract is called borrowing. So like this. We subtract, start at the right and work our way back to the left. Because 3 minus 7 can't be done. So we're going to borrow from the 8. This is a 7. This is now 13. 13 minus 7 is 6. 7 minus 9 can't be done. So we borrow here. This is a 5. This is now 17. 17 minus 9 is 8. 5 minus 2 is 3. Just like with the carryings, the borrowing is a relatively new process. One possible way that this was done before borrowing looked like this. 6 minus 2 is 4. 8 minus 9 can't be done, so we're going to take from the 4. That's a 3. This is 18. 18 minus 9 is 9. 3 minus 7 can't be done. We take from the 9. This is an 8. This is a 13. 13 minus 7 is 6. Get the same answer either way. Again, I'm not trying to change how you subtract. I'm just trying to prove a point there. I could show you 2 or 3 more ways to subtract that'll work every time. There's not just one way of doing things. Again, the calculators exist, and I'm not going to deny them. At least before you punch this in the calculator, I'd hope you look at this. You know, that's about 700. That's about 300. 7 minus 3 should be about 400. Now, what we talked about yesterday comes into these estimates as well. When we add or subtract, we keep the same name. So I had 700 and 300. That works great. They're the same name. 7 minus 3 is 4, and it stays 100. Same up here. 600 and 300, they're both 100, so I can combine them. 6 and 3 makes 9, and they stay hundreds. If I'm estimating something like this, well, if I'm rounding that, my tendency is I'm going to want to round that to 5,000 and this to 900, right? But when I go to combine that, those have different names. Now, the estimate here is still pretty easy. I'm just going to do, bring down the zeros, 0 and 9 is 9, and whatever. But technically what I'm thinking there is, this is 50 hundreds and this is 9 hundreds. 50 and 9 makes 59 hundreds. If that makes any sense. Make sure you're not, some people would jump and say, oh, 5 and 9 is 14. You can't because they're not in the same place value. They're not the same name. Multiplication. So let's do 231 times 32. This one I am going to write out in full form. 2 hundreds and 3 tens and 1 1. And this is going to be 3 tens and 2 ones. When I multiply, do I have to have the same name? No. So what that means is this 3 tens here, not only can that be combined with these tens, but it can also combine with those ones. In fact, every digit in one number can be combined with every digit in the other number, because we don't need the same name. Long multiplication is nothing more than an organized method of making sure that every digit in one number is combined with every digit in the other number. Now, the place you start varies depending on what region you're in, what country you're in, what textbook you're using. In this area, typically, we start with the bottom number, the last digit. Now, if you're in Mexico, they start with the top number, the last digit. It doesn't really matter whichever way you do it. It'll work out the same. We're typically used to starting with this digit, and we'll start out, use that with the last digit of the top number. That digit, before we're done with it, has to combine with every digit in the top number. So we combine counts. 2 times 1 is 2. We combine names. 1s times 1s is 1s. Move to the next digit. Combine counts. 2 times 3, 6. 1s times 10s, 10s, because anything times 1s is itself, right? Next digit. 2 times 2, 4. 1s times hundreds, hundreds. Now we're done. We've combined that digit with every digit in the top number. We move to the next one. What have we been taught we have to do before we move to that digit? Put a 0 here or leave a blank and move over a spot or whatever, right? So now we've got 3 tens times 1 1. 3 times 1 is 3. Tens times 1s, tens. The reason we had to put a 0 in there is it keeps our place values lined up. Our tens are going to go with our tens. Now the next digit, 3 tens with 3 tens. 3 times 3, 9. Tens times tens, hundreds. Our place values are staying lined up. 3 times 2, 6. Tens times hundreds is 1,000s. Or just thousands if you want to call them that. Then we combine the things that have the same place value. So 2 1s, 6 and 3 make 9 tens, 4 and 9 make 1,300, so 3 carry the 1, 1 and 6 make 7. So 7,392. Now I realize long multiplication is not something most people like to do by hand. So you're probably going to be looking at something like 200 times 30 is your estimate here. Now, 2 times 3 or 3 times 2 is 6, but when you multiply, you're combining the names. Hundreds times tens is thousands. The shortcut for that is you got 2 zeros and 1 0. You just combine them to make 3 zeros. Kind of we talked about counting the decimal places yesterday. You count the zeros and put that many zeros in your answer. Now you'll notice this is quite a bit bigger than 6,000. But that's to be expected because both of these numbers here were rounded down. 231 went down to 200. 32 went down to 30. So I expect my real answer to be bigger than my estimate since I rounded both numbers down. I'm not going to do a lot of long multiplication with you because, well, I know you guys are going to Most likely use your calculator on those anyway. Make sure you do a couple in the homework because there will be one or two on the quiz where you do have to do them out the long way. I do want to show you, though, some long division. And before we do that, let's talk just a little bit more about multiplication, like this. If you go back to like first grade when you started to multiply, before you memorized your multiplication facts, before you knew that 5 times 3 is 15, how did you figure out what 5 times 3 was? You could look at the table. What's that? There you go. That was 5 plus 5 plus 5. It was 3 5s added together. Multiplication is repeated addition. Technically, that's its definition of multiplication. It's just repeated addition. Now, we've said that division follows the same rules as multiplication. It's just multiplication done in reverse. So if I have 24 divided by 8, it makes sense that that is repeated subtraction. 24 minus 8 is 16. There's once. 16 minus 8 is 8. There's twice. Minus 8 again is 0. That's 3 times. 24 divided by 8 is 3 because I can subtract 8 from 24 3 times. In fact, that explains our remainder system. If I have 28 divided by 5, well, I see how many times I can subtract 5. I subtract it once, I'm at 23. Subtract it a second time, I'm at 18. A third time puts me at 13. A fourth time puts me at 8. Subtracting it a fifth time puts me at 3, and I can't subtract it again. So 28 divided by 5 is 5. I can subtract it 5 times with a remainder of 3. Now, how we express that remainder is going to vary, whether we're working with fractions or decimals or whatever. For right now, at this moment, we're just going to leave it as remainder of 3. Just 5R3 is fine. No, just R is fine. So, if I have something like 48 divided by 3, should I start subtracting 3? I could. That's technically what it's doing, is dividing by 3. It would take a long time. So a method we use is subtracting a bundles of 3. Let's subtract 10 of them. 10 3s. So 10 times 3 is 30. I subtract that, I'm left with 18, right? So I've subtracted right now 3 10 times. Now I can keep subtracting 3 here. One more time is 15. The second time is 12. How many times am I going to subtract it before I get down to 0? Well, 6 more times, right? So 6 more times is going to end up in a total of 16. So I took out that bundle of 10 of them. And now it's a lot more simple, right? A lot easier to do, a lot quicker to get there. Does that make any sense? It's a little confusing, yeah.
I just learned to memorize my times table for multiplication table.
Oh, sure. So you know that 3 times 16 is 48. So yeah, so you're doing the reverse multiplication, which is part of the definition of division. The reason I'm showing you this is the process of long division is completely based around this idea here of doing repeated subtraction. But rather than subtracting the number once, we're trying to subtract the number in big bundles. So subtracting it 10 times if we can, or 100 or 1,000 times. Let me show you what I mean by that. Let's take something like, let's do 65,287 divided by 21. I'm definitely not about to start subtracting 21 from 65,000. But if I can take it in bundles, it would speed it up. How big of a bundle? Well, I'm going to look at the place value of the first digit of the number I'm dividing. What's the place value of that 6? 10,000. What is 10,000 times 21? Careful. 210,000, right? Can I subtract that? No, that's too big. So my next place value is 1,000. 1,000 times 21 is 21,000. Can I subtract that? Yeah, in fact, 3 times, right? Should be 63,000. So I subtract that. I've got 2,287 left. How many times did I just subtract the 21? Well, I did a bundle of 1,000. Well, I did a bundle of 1,000 3 times. So 1,000 times 3, I subtracted it 3,000 times. 3,000 times 21 is 63,000. Next place value is 100. 100 times 21 is 2,100. Can I subtract that from what's left? Yes, I can. It looks like I should be able to do it just once, right? So I only did that once, but that was a bundle of 100. So I subtracted 21 100 more times. Next place value, 10. 10 times 21 is 210. Can I subtract that? Not from what's left. No, too big. So next is 1. 1 times 21 is 21. I can subtract that. Looks like only 8 times, right? 21 times 8 is 168. 19 left over. So I subtracted it 8 more times. So when I divide 65,287 by 21, the result is 3,108 with a remainder of 19.
I'm not sure exactly how I did division in high school, but something about this computer.
Okay, well, you might be looking at this thinking this doesn't look anything like what I was taught. Let me show you how it's similar. What you were most likely taught would have been this. I'm going to take the 21. Does 21 go into 6? Nope, so I'm going to leave it blank above the 6. That's what we just did here. 10,000 21s is too big. Can't take it out, so we don't have any 10,000s. So move to the next digit. 65. Does 21 go into 65? Yeah, 3 times. Put a 3 there. 3 times 21 is 63. There's 2 left over. You look at what we did over here. It's the exact same thing as without the zeros. We left the zeros off. And then here you're taught you bring down the next digits, you bring down the 2. Here we brought down everything else because we were subtracting everything. 21 goes into 22 once. You put the 2 is the last digit we use, so you put a 1 there. 1 times 21 is 21 with 1 left over. Again, just leaving the zeros off.
So theoretically, the first way is just a little bit faster.
Well, this way is a little bit faster. It's a shorter way of doing it. This is just the full form. This is really what you're doing. All of those shortcuts you were taught, this is really what you're doing right here. You're just skipping a bunch of these steps. And that's, yeah, it's abbreviated tremendously. And one of the problems I have with the way we're taught to do a lot of our math in high schools and middle schools right now is we're taught the shortcut, but you're never shown where it comes from. So you've memorized the process, but you have no idea where it comes from. So the problem is, like you said, you're not really sure how you did division in high school. Well, after a couple of years, it gets foggy. Since if you don't understand where it came from, it's a lot harder to remember it because you just memorize something. If you understand where it came from, it's a little bit easier to remember. To me, this process here, and I'll be honest, I was almost 30 years old before I saw this process for the first time. I mean, I'm obviously fairly decent at math, and all I knew was memorize and repeat. Now that I've seen this process here, the whole idea of long division makes sense. I had no idea why I did long division. I just knew it worked, and that's how I was supposed to do it. Now that I know why I do long division that way, this whole process makes sense. I'm just leaving out parts of the steps is all I'm doing. Yeah. Long division is the one operation I try not to do by hand if I can avoid it. That's the one that I will throw in the calculator every chance I get.
Seems like the most tedious.
It definitely is.
It seems like the most drawn out for
Well, and you're doing 3 out of the 4 operations. I mean, you're doing multiplication, you're doing subtraction, you're doing addition. I mean, you're doing everything there but division, really, when you do the long division process. Realistically, if I were looking at this, I'm going to punch it in the calculator. But again, I'm going to think of this. Hey, that's about 70,000. This is about 20. Now, we talked about when you multiply, you combine the zeros. When you divide, cancel the zeros. There's 1 0 that I'm dividing by, cancel 1 off of there. So this is 7,000 divided by 2. There's a couple of ways you can think of that. You can think of that, well, 7 is close to 6. 6 divided by 2 is 3, so it could be 3,000. 7 is close to 8, so 8 divided by 2 is 4, so it's between 3 and 4,000. That's good enough. I mean, estimating is something, when I talk about estimating, I'm not saying you have to do it my way. Estimating these problems is something I want you to look at and come up with a quick way that you can look at it and estimate an answer. Because the thing with estimating is there's a way that's going to be easier for you to do it, and it might not be the way I show you. If you're trying to repeat somebody else's way and it's kind of a struggle, you're going to do it once or twice, then you're going to stop doing it. You're just going to start trusting the calculator. Find a way of estimating that works for you, that you can do rather quickly and easily, that you don't mind doing, so that you're going to do it. I don't care how you estimate, as long as even if you're just looking at this and guessing, hey, 21 goes into 65 about 3 times would be 63, so that's going to be about 3,000. How you estimate is totally up to you. I just don't want you blindly punching numbers in that calculator in case it spits out one of those ridiculous answers like we saw. Now, the way I would do this, after I canceled the 0 off like I showed you, I would take the 70 divided by 2 is 35, and I have 2 zeros left. So I'm expecting an answer around 3,500. Now I got 3108, which is in the ballpark. But again, looking at, okay, 7 is going to be between 3 and 4 if you divide it by 2. You know, that between 3 and 4,000, or however is comfortable for you to estimate it. Okay, I think since there's only 2 of you here today, that's a good place to stop. We'll have our first homework out of the book, pages 8 through 10. 1 through 69, the odds. So by odds, I mean you just do 1, 3, 5, 7, 9. 2 reasons for that. One is if I had to do all of them, it would be a really long assignment. Second, in just a moment, I am going to give you a packet that contains the answers for all the odd problems. I don't want you to go home and do homework and not know whether you're doing it right or not. Because you run that danger of doing a whole assignment wrong, and now you've developed a bad habit, and you don't find out till the next day that you got it wrong. I want you to do a couple, check the answers, make sure you're doing it right so that you're doing them right as you go. Something to be said about having that feedback of knowing you're doing it right makes you feel a lot better, makes the homework go a lot easier too. Also, especially here on these first few assignments, I realize that these are easier problems. I'm not about giving you busy work. Remember, I mentioned I don't collect your homework and go through it. So if you do the first few problems, they seem easy, feel free to skip ahead a few and do some of the more difficult ones and go on from there. Don't feel like you have to do every problem. To me, the homework is to prepare you for the quizzes and the tests and to teach you. So do as much as you need to do to make sure you're ready for a quiz. Now, if your answer to that is, I know this, I don't need to do any, that's not the right answer, because it's very, very easy to be sitting in class watching it done on the board, and it looks really simple, but when you sit down to do it yourself, it can be a very different story. So make sure you are doing at least some of the more difficult problems at the end. So pages 8 through 10, 1 through 69, the odd, I will hand out that packet in just a moment.